Right, good morning Year 9. So today we are looking at the development of the periodic table. So for this little component of your GCSE, you need to know what it used to look like, how it developed to what we look at today, and where everything fits within the periodic table. There's also a little bit that you need to know about in terms of metals and non-metals and their reactivity, but we'll revisit that later on. So we're not going to do that today, because we actually revisit that in a couple of lessons time, so there's no point doing it twice. So how did the periodic table used to look? So initially the elements were arranged in order of their atomic weight. Now we call that the mass number. So the other day we had two things labelled on our periodic table. We had the top number, which was the mass number, or the number of protons and neutrons, and we had the atomic number, which is the bottom number, which is the number of protons. So originally, the elements were arranged by their atomic weight or their mass number. But this was wrong because elements were in the wrong place and there were gaps due to missing numbers. If you have a look at your periodic table, you'll see that if you look at the top numbers, there's lots of gaps. And so this periodic table didn't fit, it didn't look right, it didn't work, it wasn't in any form of working order, and it didn't actually make any sense. So this scientist came along called Mendeleev, and he arranged or rearranged the elements into groups according to their patterns of reactivity. There was quite a few things that went on in between here, but generally this is then what happened. He ignored the atomic weight slightly. They still do play a part, but we're going to have a look at a couple of examples that don't fit that pattern perfectly. So he ignored the atomic weight slightly and he left gaps because he was very aware that we hadn't found at that point every single element that was known. That wasn't known. He knew that there was lots of elements left undiscovered, and if he packed everything in solidly, then these new elements wouldn't have a place to fit. So what he did with those gaps is he predicted the properties that he would expect based on the other elements around those groups. So when new elements were discovered, they could then slot in. So now, or in terms of progression, so isotopes were discovered and new elements that matched the predictions were added. So developments in the structure of the atom helped us with the development of the periodic table, because up until that point, protons, neutrons and electrons weren't known about. Now we know about them, and we know that in terms of reactivity, we're looking at the number of electrons, and we know that to determine what atom it actually is, it is the number of protons that's important, not the mass number. We also know that the number of electrons in the outer shell is responsible for how an element will react. We are going to look at that in a bit more detail another lesson. So maybe at this point, just make a note that the number of electrons in the outer shell plays a big part in how reactive an element is. The other useful thing was in the gaps that he had left as elements were discovered. When they were reacted, they were found to have properties that actually matched his predictions perfectly. So this helped cement this idea that this periodic table was ordered in the correct fashion. And as I say, as we discovered more about the structure of the atom, it only sort of cemented this further. So just an example of how isotopes might mean an element was in the wrong place in the original periodic table. So there's two examples I want you to think about. One of them is potassium and calcium. So they're next to each other in the periodic table. Calcium has a mass number of 39. Remember, we did last lesson, that's an average of all the atoms, because there might be some that don't have a mass number of 39. They might have a slightly higher one. And we have calcium that's got a mass number of 40. So in your periodic table, they are in this order. We now have them in this order because of this bit here, but let's imagine we don't have that. So we just have the 39 and the 40. But let's say that we've got potassium, and potassium has an isotope. So actually the mass number of potassium is 41. Well, if we now look at these two, this element has a higher atomic weight or mass number So it would go calcium, then potassium, which is wrong. Because we now know about isotopes and we know about neutrons and the part they play in isotopes, we now know that actually the average mass of potassium is 39, so it goes here, and the average mass of calcium is 40, so it goes there. Another great example to have a little look at on your periodic table would be to look at argon and potassium. So on your periodic table, you read across like you would read a book. Excuse my terrible drawing, but this would be a really good example. Okay. Now, I apologise because it's now going to be sideways, but it was the only way I could fit everything on that I needed to talk about, so you're just going to have to turn the camera or turn your face. So, let's have a look here at argon, which has a mass number of 40, and here we have potassium, which has 39. So the way that you read a periodic table is you start on hydrogen, and like a book, you read across, go down to the next row, read across, go down to the next row, read across, down to the next row, and so on. You'll see that I've drawn a green line here because to be able to draw the atoms, you only need to be able to draw it to calcium. So actually anything past that, you don't ever need to be able to draw. So if we look at argon, 40, and potassium, 39, we can see there's a bit of a problem, because actually if we'd have gone on atomic mass or atomic weight, actually argon comes before potassium. But if we look at the proton number, the bottom number, argon only has 18 protons, potassium has 19. Potassium has one outer shell electron, so it's in group 1. Argon has a full outer shell, it doesn't need anything, so it goes in group 0. Again, we're going to look at these group numbers and what these mean in a bit more detail when we look at something further down the line, so I'm not going to go into too much detail about that right now. So here's your periodic table, and this is what it looks like. Again, I'm really sorry, I don't have a printer, so hand drawn it is. So there's a few little things you need to be able to draw. So we have our metals and our non-metals. So generally speaking, our metals are from group 1, 2, all the way across to group 3. You'll notice that boron isn't included in that. There's a funny line that goes like this, because actually everything this side are metals and everything this side are non-metals. Groups 4, 5, 6, 7 and 0 are non-metals. Groups go down, so we have group 1, group 2, transition metals, group 3, group 4, group 5, group 6, group 7 and group 8. Periods, repeating patterns, periodic table, go across. Now, the most common mistake that people make here, and I'm going to label this up, is that they forget that there is actually a row here with hydrogen and helium on it. So that would actually be the first period. Lithium would start the second one. Sodium would start the third one, and so on. Okay, so periods, groups, metals, non-metals. Hydrogen is a non-metal. It sits here because it has one electron, which makes it fit into group 1, but it's a non-metal, which makes it fit in over here, which is why it's bang in the middle. Some periodic tables it's added onto here, which is wrong because it's not a metal. So metals lose electrons in reactions to become positive ions. We are going to look at this in another couple of lessons' time. They get more reactive as you go down the group. Non-metals, so these ones over on this side, they gain electrons in reactions to become negative ions, and they get less reactive as you go down the group. So if we looked at lithium, sodium and potassium, just realised I'm using a pen that I've chewed. So if we use lithium, potassium, sodium and potassium, they are metals, so they will lose their electrons in a reaction, and they will get more reactive as you go down the group. So out of these three, potassium is lower, so potassium would be more reactive. In group 2, calcium would be the most reactive out of the ones I've drawn. Obviously there are more underneath. However, if we went over to group 7, these are non-metals. So actually, as we go down the group, they get less reactive. So the least reactive would be bromine, and the most reactive would be fluorine. In group 6, the most reactive would be oxygen and the least reactive, most reactive, least reactive, most reactive, least reactive. So these are just points to make a note of. So for your task today, I would like you're going to produce a timeline of the development of the periodic table using the information that's provided in the PowerPoint slides. Any questions, please just email your teachers. This is sort of an overview and we're breaking each thing down. So for example, we're going to look at this idea of losing and gaining electrons. We're going to look at this idea of getting more and less reactive as you go down and up the groups. We're going to look at what the actual structure of them are. So don't panic, this is a bit of an overview to start with. The main point of today's lesson is the development of the periodic table, how we got there, and sort of what it actually looks like today.